Okay, so in today's lecture, we'll start again with announcements, and then we'll get into combinational logic design part 1. We'll continue our discussion on encoders. Homework 6 is due tonight on Gradescope, 11:59 p.m. So please submit that. Many of you have already done it, so that's good. Studio 5 is due next week. So, if you use the help sessions on Sunday as well as Tuesday to work on the studios and get them checked off even before Wednesday, if some of you can do that, that will be a good idea, so that there is not too much, it's not a bottleneck on Wednesday. But it is due the next Wednesday, October 28th. Quiz 14 is available on Gradescope for you to answer. There are 4 questions, but if you can answer those questions after the lecture, I think you guys will do well on it, because it has some questions about what we are going to start talking about today. Let's see, that's as far as announcements are concerned. Let's move on to the priority encoder that we have been talking about. So this is 74X148. The design, the Studio 5 has one of the tasks that is related to this. So on the left, we see a priority encoder that we were using to formulate general ideas about an encoder, which is, if you have a 8 to 3 encoder here, 8 inputs, 3 outputs, well, 4 outputs really, but 3 of them are data outputs. One of them is like a status signal output. All the inputs and outputs in this case are active high as shown. And we said the priority encoder is going to first encode the input sequence into a binary representation of that value. So for example, if I6 is active, it is going to make the output 110. It's essentially going to encode the input sequence. The criteria here is that only one of the inputs can be active, and because it's the user's responsibility, the user might mess it up, which means that there should be some mechanism inside the chip itself that makes sure that we have some sort of priority. We are going to prioritize one input over the other. So the priority that we use is of the highest, most significant bit that is active. So if I7 were to be active, we would essentially ignore all the others. And if I6 were to be active, we would ignore I5 through I0 and so on. So we would give priority to the most significant bit that is active and encode that, generate the output bits based off of that. The idle output over here is essentially used to figure out whether you have any active input or not. Now, in a real chip, which is of the part number 74X148, again you have, let's see, you have 8 active low inputs. 8 active low inputs. We have 1 active low enable signal. We have 3 active low outputs. Those are our encoded outputs. And then we have 2 other special outputs. It looks like you are right. So let me okay, so I hope that it came back in. All right, so let's see, 8 active low inputs, 1 active low enable, 3 active low outputs in A2, A1, A0. And the good thing here is that the numbering of the inputs and outputs is indicating the most significant and least significant input and output. So for example, if I write that for the inputs, this is going to be my most significant because the index is 7. Come on. Yep. All right. So let's see if this holds up. I0 is our least significant input. I7 is our most significant input. And in terms of outputs, A2 is going to be the most significant output and A0 is going to be the least significant output. And the indexing on the name itself is indicating that. Now let's talk about the two other outputs here, which is GS, which stands for got something, and EO, which stands for enable output. So got something is an active low output, which is used to find out whether the chip has any input that is active or not. Did you get something or not? Right? So no matter which input is active, it is just used to find out whether you have any input active or not. The enable output is another active low output, which is used in cascading. Used in cascading. It's very similar to got something, but has dependence on enable. So we'll get some clarity on this about the difference between got something and enable output once we look at the truth table of this design. So let's take a look at that. This is part of your Studio 5 write-up as well. And over here we have our 8 active low inputs, I0 underscore L all the way to I7 underscore L. This is written in slightly opposite order of what we are used to. We are used to putting the most significant all the way to the left. We are used to writing the least significant input all the way to the right, but that's okay. We just switch the order, but we know what it is doing, what its purpose is. The leftmost column is the enable input, which is an active low input. So for the first case, the chip is disabled because EI underscore L is 1. So that's disabled. So when it is disabled, the chip is disabled, no matter what you have for the inputs, XXXXX, all the outputs are going to be inactive, 111. Note that they are active low outputs. You did not get anything, so got something is also low. And the enable output is also low, so you do not enable the output, which is used for cascading multiple 74x148 chips. So that's when enable input is inactive. That's when it is off. Now for all the other cases, we have enabled the chip. EI underscore L is low, 0. We have enabled it. Now when it is enabled, there are multiple things that can happen. The most significant bit might be active. If that is the case, we will ignore all the others because the priority is set by the most significant bit, which is active. So if I7 is active or I7 underscore L is active, then we ignore all the others below it. And in the same manner, we go down this list all the way down to the possibility that I0 underscore L could be active. Those 8 input situations are encoded as low, low, low. That's for 7. Low, low, 1. That's for 6. And so on, all the way down to 1, 1, 1, which means inactive, inactive, inactive. That's for the last case. Now, what is common to these 8 situations? For these 8 situations, you got something. The chip got something. Hence, the got something underscore L output is active. Now, the question is, when is got something underscore L active? Is it active only when I7 is 0? I6 is 0? I5 is 0? So, the question I'm really asking is, the got something underscore L, the got something output, is it active only when one input is active or not? Well, it turns out got something underscore L is active when one input is active, or some other inputs could also be active, right? Because I6 could also be active at this point, but it will give priority to I7. So got something is simply, did you get at least one input active or not? But for the last case, when no input is active, our got something underscore L output is inactive. Note over here, the enable is active as well for the last case. Now let's go to the enable output underscore L. When do I enable the next chip? If I were to cascade 74x148, I will enable the next chip when I have a 0 over here. When do I get a 0 over there? I get a 0 over there when the chip is enabled and you did not get anything. No input is active and the chip is enabled. That's when you are going to enable you are going to make the enable output active. So if I go back over here and see, if you have another chip, right, that you are using to cascade, you could use this as an input to that guy, EI, right? So if you have multiple chips like that, multiple 74x148 chips like that cascaded, you could use the enable output of the first chip to be connected to the enable input of the next chip. That way you can design bigger encoders. So for example, if you wanted to design like a 32 to 5 encoder, then you could use 4 of these. But you would have to cascade them using this enable output and enable input signals. That's what it is used for. All right, let's go back here. Now another difference, between enable. So for enable output and got something, the difference is the enable signal, right? So when the chip is disabled, got something is off and enable output is also off. But when the chip is enabled and you don't get anything, got something is inactive, but EO, the enable output, is active. So that's the difference there. Questions about this? Okay. Let's move on to the conversation about tri-state buffers or 3-state buffers. Here, the output can be low, we are used to seeing that output being low. The output of a buffer can be high. We are also used to seeing that, low or high. But it can also be in a third state, which is called high impedance state. So the high impedance state is simply indicative of the output being a dangling wire. It is not connected to anything. High impedance or a dangling wire, which means it is not connected to anything. It has three inputs and outputs. You have enable. Let me write it in, well, this is your enable input. A is your input, out is your output. When enable is 1, then output will equal A. That means if this was a 0, this will be a 0. If this was a 1, this will be a 1. As long as enable is 1, it is enabled, right? The figure, the symbol itself indicates that everything is active high. The other possibility is enable being 0. So if the tri-state buffer is disabled, then no matter what A is, the output is going to be in the high impedance state. It is going to be a dangling wire, which means just imagine like a disconnect, physical disconnect of that output wire from the buffer itself. It's not connected to anything right now. This wire is a dangling wire. That only happens if the tri-state buffer is disabled. So I've color coded them as in red and blue to indicate the two combinations of the enable. All of this is captured in a truth table over here for the tri-state buffer. When enable is low, you see this, when enable is low, that means the tri-state buffer is not enabled. No matter what A is going to be, the input, the output is going to be in the high impedance state, a dangling wire, not connected to anything. When the tri-state buffer is active, enabled, then low goes to low, high goes to high, exactly like a buffer operates. So maybe we can just write this. This is like a buffer. And this is not connected. Output is not connected. So that's your tri-state buffer. And what it is really used for is to connect multiple outputs together. So the real application of a tri-state buffer is to tie multiple outputs together. Because if there are multiple things connected to one common bus, for example, then you cannot allow the multiple outputs to gain control of that one bus. You would want to have some sort of mechanism so that only one person can write to it. That's why this is used for. All right, there are different flavors of the tri-state buffer, and it has to do with active low and active high combinations. So for example, for the first case, we have active high enable, and for the next case we have an active low enable. For the third case, you have an active high enable, and last case you have an active low enable. But with that active high enable or active low enable, the first one is a buffer because it's not changing the input state. Input A will be going straight to output. if it is active. The second one is also a buffer, but with an active low enable. The third one is actually an inverter, a NOT gate. And the last one is also an inverter. So you see, you can have these four combinations where the enable signal could be active high or active low, but the buffer itself could be a buffer or an inverter. So once you look at this, let us write a truth table for one of them. So let us pick, let's see, maybe we can pick this last one. Let us try to write the truth table of this guy. You have enable underscore L, active low enable, input is A, output is what? Out underscore L. Enable underscore L could be low, and when it is low, A could be low or high. And when A is low or high, you see it is enabled here, so it's going to invert high and low. That's when the chip, the tri-state inverter is enabled. Next, you have the possibility that enable underscore L could be high, which means that it is actually disabled. So no matter what A is, the output will be in the high impedance state. So in this manner, you can probably write, we have already written this on the previous slide, but you can also write the truth table of these two tri-state buffers. Questions about the different flavors of buffers? What their symbols mean, and whether you are able to write the truth table of each of them. So they are all high impedance high. So it depends, like high output as off. I didn't quite understand that. So it depends on, are you talking about a specific symbol? There are four of them here. So let me do this. Let me talk about the case in which the outputs of these symbols are going to be in high impedance state. They are going to be in the high impedance state only when I make this 0, or I make this 1, or I make this 0, or I make this 1. Only then the outputs are going to be in the high impedance state. For all the other cases, they will be either equal to A, the input, or be equal to A complement. Does that answer your question? Can you define high impedance? Suppose I take a wire from some point, and I'm calling that VA, voltage at that point, to be VA, and I connect it to a plus 5 volts power supply using some resistor R. What is going to be VA? what will I measure at VA? Five volts, perfect. However, if I don't connect anything here, suppose I just say, all right, nothing. I don't connect anything here, then what is going to be the voltage now? That nothing is called high impedance because it's just a dangling wire, right? Because I did not connect it to ground. Yes, absolutely right, because it's not grounded. Does VA not change with... It doesn't matter what that resistance is going to be. Suppose I use the same resistance in the previous case for 5 volts and now it is not going to matter. In the previous case it is going to measure 5 volts. Now it is not going to measure anything because it's not connected to anything. Yes, undefined. All right, let's see. So, think of here. Let me go through an application of the high impedance, the tri-state buffer, and you guys will really see how it can be used. So let me move on to the next one, and with this slide, I'm pretty sure you guys will be able to understand what we are talking about here. So there are two things. Mainly there are two things here. One is the 3 to 8 decoder. This guy is our 3 to 8 decoder. Active high inputs, active low outputs, and 3 enable signals. One of them is active high, 2 of them are active low. We have seen this before. Now suppose I connect the 8 outputs of the decoder to the enable signals of 8 tri-state buffers. I have 8 tri-state buffers here. Their inputs are some arbitrary input signals. PQR, earlier we used A, now we have PQRST, UV, W. And all those tri-state buffers are trying to write to the same wire, S, or serial data, S data. They're all trying to write the same thing. They're all trying to write maybe at the same time. Now, I hope you see that kind of sharing in terms of writing to one wire, one common wire. In our case, it's a 1-bit party line. Is going to have problems, right? What if R is trying to, what if this input R is trying to write 1 to it, and what if this input S is trying to write 0 to it? What is going to happen? Well, we are going to have a short circuit there. So we cannot allow multiple variables. Let me just define PQRS here first. So what is P, Q, and so on to W are arbitrary binary variables or inputs that want to share or write to the 1-bit party line, right? So all these guys are trying to write to it. P, Q, R, S, T, U, V, W. They're all trying to write to it. But I cannot allow more than one. I can only allow one guy to be able to write to it at any given time. Which is why I'm going to use my friend 328 decoder that guarantees that only one of the tri-state buffers is going to be active at any given time. So let's do this exercise. Let me just put some arbitrary inputs, and you guys will be able to see how this functions. So let me associate this guy to be a 1, this guy to be a 0, this guy to be a 0. So I've essentially enabled my chip. Next, I'm going to make 1, 1, 0. I have associated source 0, source 1, source 2 with three values, 1, 1, 0. For the A is most significant or least significant. Yeah, here it is. You see this? 0, 1, 2. So sometimes you got to pay attention to the name of the signal itself to find out which one is most significant. Clearly, you see SSRC2. Why 2? Because it is the most significant input. Here it is the least significant. Right? So the numbering itself will give that, give it away. All right. Now, if this chip has these inputs, I want you to tell me which output is going to be active now. You can use either the pin numbers to tell me which one is active, or you can use Y0 or Y1, something like that. So everybody is saying Y3, right? It is enabled, so that's good news. And I'm going to read ABC as 0, 1, 1. So if it is 0, 1, 1, Y3 is going to be active. Perfect. So I'm going to use blue color for this, for Y3. Is there anything else going to be active? How about Y0, Y1, Y2, Y3, Y0, Y1, Y2, Y4, 5, 6, nothing else, right? So I'm going to maybe use a different color for that. Inactive, 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 inactive. You see, the decoder made sure that only one output is going to be active. Now, using this, you tell me what this is going to be. S data is going to be. S is absolutely right. Because only this guy will be able to write to the 1-bit party line. Nobody else can write to it because they're all disabled, right? What does disabled mean? I said dangling wire, remember? So all these are cut off from the entire circuit. They are essentially cut off, and only the tri-state buffer that is enabled, which is this blue line here, only that particular input S will be able to go through to the party line. So that's the only thing that we will be able to write to S data. Now let's do another exercise. Let's go do this. In blue, let's do this. How about that? I've changed the input sequence. I've left it enabled. Who takes control now? No, all the way at the end. You can tell me all the way at the end. Q is absolutely right. Now, just for the fun of it, I will do this. What I'm going to do is I'm going to show you guys something that was very interesting that I wrote for one of the exams with this. you see what I did here? Instead of having one, give me 1 second, Preston. So instead of having one 74X138 chip, I connected two 74X138 chip. That was essentially what we did to design a 4 to 16 decoder using cascading. And then I connected the outputs of all the 16 outputs to 16 tri-state buffers. And the problem that I gave was, so this was spring 2019. What the problem that I gave was, I gave them the sequence of inputs. I gave them N0, N1, N2, N3, some arbitrary values when it is disabled, and for all the other cases it is enabled. And I said, what is S data going to be? And it turns out the way we said Q and S, this particular combination spells out correct. So I thought that was very nice, that you solve this problem and you got a correct answer because the answer is correct. All right, let's go back and let's take the question. If Q is on versus S is on, doesn't S data get the same result? Well, if Q is on, right? If I hope you mean this is on. Let's not do the entire thing. So if this guy is active, then everything else is inactive, right? The decoder is going to take care of it. Does S data read Q or 1? Well, it depends on what Q is. So these are all variables, right? So P, Q, R, S all the way to W, these are all variables. They could be 1, they could be 0. Preston, you can go ahead and use your mic. I think I'll be able to understand your question better if I hear it from you.
Hello?
Yeah.
Okay, so basically what I mean is, like, let's just say S data is like going to the computer. So is the computer reading the letter of whatever variable is on, or is it just reading the voltage being high, like a 1?
It is reading one of these 8 values.
So
Now,
it can tell them apart?
Oh yeah, so because P, Q, R, S all the way to W, these are binary variables, right? So they themselves could be a 0 or a 1.
Oh, okay, got it. But like, it was just confusing because they all share a line, so like, just assuming like it's a voltage, right? And
Yes.
all the others are on 0.
Right.
Wouldn't
But
the voltage reading be the same no matter what?
yeah, but no matter what the others are, only one guy will be able to control S data, right? So
Yeah.
it doesn't really matter what others are. Only one variable. Say for example Q. Only Q can take control of the party line. Now if Q is 0, S data is 0. Q is 1, S data is 1.
Okay. Yeah, I guess Tyler summed up what I'm trying to ask pretty well too.
Whether it can tell the variables apart or if it is just
Like, is S data just reading a 1 or a 0, or is it...
it is reading only a 1 or a 0, but though that 1 or a 0 in a problem is associated with a variable, right? So PQRS, this could be 8 switches, right? So it could be 8 switches. And S data, suppose you have that as a LED, right? So
Right.
is the LED going to be on or not? Well, you have to tell me what Q is. Is the switch on or off, right?
Yeah. But wouldn't it be like if any of them are on?
So only one guy has to be enabled, right? So only one
Yeah.
switch can control that LED. The decoder is going to take care of that.
Okay, I might be overthinking this.
So, there is no need for S data to distinguish between P, Q, R, and so on.
Got it. Yeah. Okay.
Because it's the user, it's the designer who is trying to perform some logic, design some logic. So that it's the user, the designer's business, right? Like the S data
Yeah.
doesn't care. Yeah,
Okay. Thanks.
no problem. Could be anything up to the designer. Yes. All right. So, are there any other questions here regarding this? Are the variables signals? Yeah. So these are all digital signals, right? Like ABC, uh, like any input or output. These are all binary signals that can take a value of low or high. In this case, P through W, these are all inputs. S data is an output. Would the variables be signal? Yes, the variables are binary signals that can take a value of 0 or 1. Some of them are input, some of them are output. Thank you, Tyler. Is there a limiting to cascading? Cascading in terms of this design, or cascading in terms of um, the the decoders, or cascading in terms of encoders? Which one? Well, in general, there are no limits to cascading, because each of them individually is being powered up by a 5-volt source and a ground supply. So if individually they're all getting their power, then there is no fan in and fan out limit I need to worry about, because they're all voltage wise, they're all going to be okay. Would having more increase the amount of time? Well, if you, not necessarily. If for example, over here, the first chip and the second chip, they operate at the same time because it's the same level. But if it is one after the other, serial cascading, then you will have that problem of a delay. But if things are happening in parallel, then there is no delay, because these two are essentially operating at the same time. There might be other problems. For example, the size it occupies on a chip or a board, that might be a problem. The complexity increases, that could be a problem. But I don't see any other limitations. All right, let's move on to tri-state drivers. Now, this is a 74X541 chip that is going to essentially buffer 8 things at once. What does it have? It has 2 active low enables, and we will see how we can use them in a very intelligent way in a little bit. There are 8 inputs, all active high. 8 active high inputs. that can go directly to 8 active high outputs. So let us take a look at the design, right? This is what is inside the chip. All of this is inside the chip. So let's take a look. I want it to be enabled. So if I want it to be enabled, I would want this to be 0 here and I 0 here. If the both enable inputs are 0 and 0, that will make it 1 and 1 here, and that will make it 1 here. And that particular one is actually connected to the enable input of all these buffers. These are tri-state buffers that are using Schmidt trigger technology, right? So they are come on. Okay. So these are 8 tri-state buffers that are operating on a Schmidt trigger technology, which essentially means I have an upper threshold, lower threshold, so I can be ignoring some of the noise that is around 0. So we talked about that when we had the Schmidt trigger discussion. But it's essentially a buffer. So if it is enabled, like here, all the outputs Y1 through Y8 will equal all the inputs. So you can say it like this: when enabled, YK equals AK. When disabled, YK equals high impedance. So this is to buffer 8 bits of data at once. All right, let's move on to the next one. Now this is how you can use 2 of the same chips. These are 74X541, 74X541. So there are 2 of them. There is a microprocessor that is able to control whether these tri-state drivers are active or not. So there are other things in this as well. There are 2 input ports. So there's an input port 1, input port 2, and this could be any port that you can have on your connected to a computer. User inputs are over here for both the chips. Now let us go through this. Let us try to answer which set of user inputs to read from. So the way it is right now, the microprocessor should have the ability to read from input port 1 and input port 2. So the question is, how should I set it up so that it reads from input port 1? What should I have? I should make this 0. Why? Because this guy is for input port 1. So I should make the first one 0. How about the second? Input select 1. I will also make this 0. And all the others, I will leave them as 1. Right? All the other input selects, there are only 2 of them here, but the design is being shown for a general case. So if this is 0 and this is 0, then this chip is enabled. However, if you look here, because of this being a 1, this is a 1 there, and this is disabled. So who takes charge of this 8-bit bus? This is an 8-bit bus. Well, these user inputs are going to now take charge of the data bus, and that data bus is being read by the microprocessor on these lines. So what should I do in order to read from input port 1? I should make this 0. I should activate input select 1, and I should disable all the other input select signals. That those are coming from the microprocessor. Once I do that, user inputs from input port 1 will go through the data bus into the microprocessor, and that's how you can read from user input port 1. Now if you wanted to read from input port 2, what would you need to do? What would you need to do in order to read from input 1100? Would you change this? Would you change read signal? Zero one zero one. 0101. Right, 0101 is looking good. This should still be 0 because you are still reading. Input select 1 to 1. Yes, you don't want user input port 1. You do want input port 2, so you have to make that active. And then everybody else is 1. If you do that, then these user inputs will take charge of the 8-bit bus, and that can be read into the microprocessor. You can see it. So this is just a way to use that 74X541 chip to be able to write to a common 8-bit bus. Let's see, what is the point in putting a NOT in front of the enable for the 74X? Do you mean this? Okay, so wherever you see a NOT, right, it has to do with the designer preferring an active low input. Now, it could be for many different reasons. One reason is input buffering. Money is always the case, but it could be due to the fact that input buffering, right? So I want to have buffers, so I can have a buffer by simply having a buffer, or I can have a buffer by using an inverter. Now, if this guy is an active low output, I can hook it up to an active low input in this case. Because otherwise, I would have had to invert the read output. So it ends up in money. Preston is right, but logically speaking, it has to do with what you are connecting to what. So if they are active, the designer looks at this situation and says, all right, it would be easier for me to have a 2-input NOR gate than a 2-input AND gate, right? All right, I hope that answered your question. Let's go on to, we did this. Let's talk about this. Because of NOR synthesis being easier, right? NOR in synthesis being easier, cheaper, universal, less transistors, all those things. All right, let's move on here. Now what we have here is a tri-state transceiver. Transceiver means I can transmit and receive. So transceiver is transmitter and receiver. So this particular chip 74X245 can move data this way or this way, A to B or B to A. It can operate as a transmitter or as a receiver. So let's go through this exercise, and what we'll do is we'll try to find the direction, right? So we have an input dir, right? So we'll make dir equals 0, and we'll try to find out the direction of movement, and we'll also make dir equal 1 and find out what goes to what, right? And in both these cases we will assume that the chip is enabled. So what I'll do is I will start off with the first case, dir equals 0. We'll start with that. So I'm going to zoom in on this part, and I'm going to say dir equals 0 here. G underscore L, I said we have to assume enabled, so I have to make that 0 as well. If those two are 0 and 0, this guy is going to be 1 here, this guy is going to be 0 here, which means this guy is going to be a 0 there. How about the output of the bottom chip? That is going to be a 1 there, that is going to be a 1 there, that is going to be a 1 there. You guys with me so far? Now, I am just going to take this guy, this 0, and write it everywhere on that line. So for example, this guy, this guy, this guy, and last one. All of them highlighted in yellow. And because that is 0, over here it is 0, that means that all the tri-state buffers that are pointing right, those are all going to be disabled, right? So if they are disabled, I will mark them as maybe red, cross. Disabled. But what is enabled? The things that are in blue. So this guy is enabled. This guy is enabled. Enabled, enabled, enabled. All these are enabled. The blue lines. So tell me, what is the direction going to be? Right to left or left to right? A to B or B to A? In this case, direction is 0. Right to left, B to A. Perfect. That's absolutely right. B to A, right? You see this? You can take any one of the cases and you can see B3 can now go to A3 because this particular tri-state buffer is enabled. This guy is disabled, so that's cut off from the chip. And similarly, we can do the other case. Direction equals 1. So when direction equals 1, let me do that in blue here. It is still enabled, so G underscore L is still 0. But what you have here is this guy becomes a 1 there. So this guy becomes a 1 here. And because of this guy changes to a 0. So this guy changes to a 0. So you see what happened? Everything got reversed. right? So all the tri-state buffers that were active now are inactive and vice versa. So what is the direction here? dir equals 1. Left to right, right to A to B, right? So you can move things from A to B or B to A by using this 74x245 chip. All you need to do is enable it and provide the appropriate direction. That's it. All right, questions about this, guys? Color coded pens is a must in this class. Yes. What does the X mean in the chip names? Chip names. Oh, 74LS245, 74SN245, 74HC245. So these are acronyms for the technology that is used to design the chip, and depending on the manufacturer, that can change. There are many other combinations. I've just written out 3 of them. But when you look at the number itself, 74 and 245, that is what the operation we are talking about. All right. Other questions, guys? Who is the busy? Texas Instruments. TI. Analog devices too. Analog devices and TI. For analog devices of TI, maybe I am not 100% sure. I know Xilinx CEO is from RPI, but I didn't know for TI. Okay, let's move on, guys. Actually, I'll stop recording here because I need to start another lecture.